All right, hello. All right, folks. So thanks for coming. Armando put together, I guess, is this slides here? This thing is click, 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 click. Yeah, so Armando put together some slides for here. If you're not aware of what Cloudflare is, then, well, I don't know. This is not, we're right there in that one of those cities. Cloudflare has data centers around the world. I'm sure folks here are pretty aware of what Cloudflare does, but we're a service that helps accelerate and secure websites and web presence, web services. And Cloudflare is used by quite a lot of the internet. So a large percentage of websites and web services use Cloudflare. We like to think of Cloudflare as bringing to smaller websites and small services things that usually are only reserved for like the internet giants. So security teams, performance teams, optimizations, you can really kind of outsource that to us. And how does Cloudflare work? Well, we sit in front of traffic. Stuff comes in, we look at it, proxy it through if it's good, block it if it's bad. A little bit more than that, but it's relatively magical for folks who are not extremely adept technically. In any case, Cloudflare has several services. This is some IoT thing. We do a lot. There's quite a lot. If you want to know more, there's several Cloudflare people here who can chat about it. But this isn't really what the meetup is about. This is we're here to have two really interesting talks about cryptography or cryptography-related topics. And we've been doing this talk series for a while. We're trying to reboot it after several years of laying off, but we've had some really great speakers, and we're really proud to have two speakers here again. This is advertising. Cloudflare's hiring. A lot of people are hiring. So check out Cloudflare's research team, research.cloudflare.com. So with that out of the way, let me introduce Emma Dauterman, who's going to be talking about True2F, which is a really cool project in the authentication space. So here you go. Let's give her a round of applause.
Okay, thanks so much. So I'm going to be talking tonight about True2F, a system for backdoor assistant authentication tokens. This work was done with Henry Corrigan-Gibbs, David Mazieres, Dan Bonet, and Dom Rizzo at Stanford and at Google, and the paper appeared at IEEE Security and Privacy last spring. So as you're probably all aware, hardware authentication tokens are a particularly effective form of second factor authentication, with U2F tokens being particularly popular. Since Google mandated that all its employees use these security keys, they haven't discovered a single instance of corporate credential theft, showing just how effective these tokens are. So what does this protocol look like? There are two steps: registration and authentication. So just at a really high level, a user runs registration when they want to log into their, or when they want to associate their token with some account. So the server sends some identifier to the token. The token then generates some server-specific key pair and sends the corresponding public key back to the server. Then they can run authentication when they want to log into their account. So here, the server sends some identifier along with a challenge to the token. The token then signs this challenge using the secret key that it generated at registration and sends a signature back to the server for verification. So in this way, U2F provides a really strong defense against phishing attacks as well as browser compromise. So in particular, even if malware takes over your browser, it can't authenticate without interacting with the token. So U2F addresses the case where the browser is compromised or there's some external attacker. But what about vulnerabilities in the token itself? So we're trusting this token to store our cryptographic secrets, but there are several reasons this token might not be entirely trustworthy. So it might have implementation bugs, or it might be subject to supply chain tampering. So implementation bugs are a very real problem. In 2017, a bug was discovered in the Infineon random number generator, which affected a wide variety of products, including Estonian smart cards, Chrome TPMs, and the YubiKey PGP functionality. And just this last spring, a bug was discovered in the randomness generation on the FIPS keys at Yubico. So these things happen a lot. They're especially difficult to deal with when they happen to supposedly secure hardware. And we'd like some way to mitigate this. Supply chain tampering is another real problem. We know from the Snowden leaks that this actually does happen. On your left, you can see a photo of the NSA installing implants in Cisco routers. And we also know that users are actually concerned about these types of attacks. So when Google released its Titan security key the other summer, there were calls from security experts for greater transparency into the supply chain process, as they were concerned about these types of supply chain attacks. So this concept of supply chain attacks can seem a little bit abstract. So I'm just going to walk through what this might look like for a U2F key. So let's say you buy some U2F key at some questionable online website, and unbeknownst to you, the attacker has built into this key, has built into this token some secret key that they also know. So now you register at github.com, and the token is actually going to register using this public key that's also known by the attacker. So now if the attacker is able to phish your password, they can actually authenticate as you, because when the server sends some challenge, the adversary can actually sign this challenge using the secret key that the user registered with. So we can see this totally breaks the security of the U2F protocol. So we want to address both these challenges, so both implementation bugs as well as supply chain tampering. And so we present True2F, which provides the same protections as U2F, while additionally protecting against faulty tokens. So we want to have the same protections as U2F. So to address the case where the browser might be compromised, the browser should learn no additional secrets. All the cryptographic secrets should remain entirely on this small piece of hardware. However, we additionally want to protect against the case where the token might be faulty. So to address the case where the token is faulty, the browser should enforce its correct behavior by preventing it from leaking secrets. So in this way, we handle the case where where either the browser is malicious or the token is malicious. So to do this, we have the 3 goals. So the first is to augment U2F to provide a strong protection against faulty tokens. So we want to have the same protections as U2F, even if the token is buggy or backdoored. We want to do this in a way that's backwards compatible with existing U2F servers. So this should only require changes to the token and the browser and not the server, since it's not actually that feasible to go around and change implementations as servers. Finally, we want to do this in a way that's practical on commodity hardware tokens. And so to do this, we implemented this on some Google hardware, and I'll be showing you the numbers later on. So to achieve these 3 goals, we adopt the following 2 design principles. So first, both the browser and the token should contribute randomness to the protocol. This ensures that the token isn't using some bad source of randomness built into it, but also that the browser doesn't know all the secrets on the token. And second, the browser should be able to verify all deterministic token operations. So wherever possible, the browser should be able to check the token's work. So we also implemented True2F on Google hardware. I'll show you the numbers later on here. So the U2F protocol has 2 steps, registration and authentication. And in True2F, we add an additional step, initialization, which you run after purchasing a token and before registering it with any website. And I'll explain some modifications that we make to registration and authentication as well. So I'm going to start off by talking about initialization. And here, the idea is that both the browser and the token should contribute randomness to the protocol. So in initialization, we're essentially going to run some collaborative key generation protocol between the token and the browser, at the end of which the token holds the master secret key and the browser holds the corresponding master public key. So why do we need to generate this key pair collaboratively? Well, if the token generates it on its own, it could be using some bad source of randomness. We also don't want the browser to generate it either, because all the secrets should remain entirely on the token in case the browser is ever compromised. And so this is why we need the randomness from both the token and the browser. So we want the following properties for our initialization routine. So first, the token shouldn't be able to bias the master public key. This is to address the case where the token has some bad source of randomness. And second, the browser should learn nothing about this master secret key. So there's actually a protocol that already does this by Corgan Gibbs et al. However, it's pretty slow on the small embedded device that we're working with. And so we present a protocol that reduces the number of group operations by 3x, which results in roughly a 3x speed up on the small embedded device that we're working with. So now I'm just going to walk through the protocol. So here we're using some group G of prime order Q, in particular the NIST P226 curve, just per the U2F spec, and ECDSA key pairs having the form of X and G of the X. So the browser starts off by choosing some values R and V, and then commits to them by just sending the hash of R and V to the token. The token then randomly selects some value V prime and sends G to the V prime, or just big V prime, back to the browser. The browser can then set its master public key to be big V prime times G to the V. So the master public key is of the form G to the V plus V prime. The browser then opens its commitment to the token and sends back V and R. So the token can then check that the commitment it received earlier matches the hash of V and R, and then set the master secret key to be V plus V prime. So at the end of this, the token is holding some master secret key of the form V plus V prime. Browser is holding some master public key of the form G to the V plus V prime. So the first property we wanted is that the token shouldn't be able to bias the master public key. And here we get this because the token chooses V prime, but the browser chooses V. And the token doesn't actually know the value V until after it's chosen V prime. And the second property we wanted is that the browser should learn nothing about this master secret key. And here we get this because the browser knows V and G to the V prime, and from that it can't learn V plus V prime. So that's initialization. I'm now going to move on to talking about registration. And here the idea is that the browser should be able to verify all deterministic token operations. So just as a reminder, in U2F registration, the server sends some identifier to the token. The token then generates some server-specific key pair and sends the corresponding public key back to the server. So we can imagine some implementation bug that undermines the security of registration. So for example, the token could generate this key pair using some weak source of randomness. So now, when the token sends back its public key, if the attacker can get this public key, it can actually derive the original secret key, which obviously undermines the security. So we can also imagine a supply chain attack mounted against registration. So for example, let's say some attacker who has built your token is able to get you to register at evil.com, which they also control. So now when you go and you register, the token is going to choose some public key for evil.com that hides the secret key for another site, maybe the secret key for github.com. It sends this bad public key back to the server, and the server is actually able to extract information about the secret key for github.com from this bad public key. So the server is essentially using this public key to exfiltrate information, essentially using it as some sort of subliminal channel. And so we'd like to disallow both these cases. And so to do this, we introduced this new primitive we call verifiable identity families, or VIFs. And these VIFs are going to leverage the master key pair that we generated at initialization. So you might be wondering, well, we're just generating key pairs on the token. Why can't we use the same collaborative key generation protocol that we used at initialization? Well, the problem is that the token actually has a very small amount of storage space, and we don't want to bound the number of sites that a user can register at. So instead, we would like to be able to derive this key pair whenever we need it. And these VIFs allow us to derive these server-specific key pairs in a deterministic and verifiable way from a single master key pair. So we're not limited to the storage space on the device. So we want the following properties from these VIFs. So first, the token should be able to produce the unique key pair for a server. This is important because the token should be able to leak information through the key pair that it chooses. Second, the token should be able to prove to the browser that the public key it selected is really the unique public key for that site. So the browser should be able to check the token's work. Third, the browser shouldn't be able to forge a signature into the public key it receives. If it could do that, obviously it could authenticate without interacting with the token. And finally, the server shouldn't be able to distinguish the public key it receives from a random ECDSA public key. So we don't want to allow the servers to be able to link tokens between accounts. So these are the properties that we want. I'll explain a little bit why that notion of unlinkability is weak later on. So I'm just going to walk through a simplified version of our VIF construction. Again, I'll talk about why it's simplified later. So here, we're again using some group G of prime order Q. And we're going to use the master key pair that we generated at initialization. And I'm going to rewrite that as X on the token in big X, or just G to the X at the browser. We're then going to use these values to calculate this new key K, which is just the hash of big X. And now I'm just going to walk through the protocol. So here, the server sends some identifier to the token. The token is then going to compute this value alpha, which is just the PRF keyed with K of the server identifier. The token then sets its secret key to be alpha times X, and its public key to be G to the alpha times X. The token sends its public key back to the browser, the browser can then also compute this value alpha, and then check if alpha is correctly incorporated into the public key. So the public key should be of the form big X to the alpha. If this is the case, it knows everything is okay and can send the public key back to the server. So the first property we wanted was that the token should be able to produce the unique key pair for github.com. And here we get this because this value alpha is unique for each server identifier. It's just the PRF, keyed with K of the identifier. Second, the token should be able to prove to the browser that this is actually the correct public key. And here we get this because the browser can also compute alpha and check that alpha is correctly incorporated into the public key. So it's the master public key raised to the alpha. And third, the browser shouldn't be able to forge a signature into the public key. Too much to explain in a talk. You can see the proof in the paper for details. And finally, we want some notion of weak unlinkability here, where the server shouldn't be able to distinguish the public key it receives from random ECDSA public key. And we can get this property because the server can't compute this value alpha, and so can't see that all the key pairs that it's receiving from a token are derived from the same value, are derived from the same master public key. If it had this value K, it could just divide out alpha. However, we might want a more complete notion of unlinkability. So maybe we want the browser to not be able to generate public keys without interacting with the token. And so in our paper, we formalize this notion of unlinkability more fully. And the protocol we present there, actually, we can actually get this more complete notion of unlinkability. So just to hint at it, instead of computing this value alpha with a PRF, we actually use a verifiable random function, where the browser can't actually compute alpha without interacting with the token, but can verify that the token actually computed alpha correctly. So that was registration. I'm now going to move on to talking about authentication. And here, the idea is that both the browser and the token should contribute randomness to the protocol. So just as a reminder, in authentication, the server sends some identifier to the token along with a challenge, and then the token actually signs this challenge using the secret key from registration and sends a signature back to the server for verification. So just as a quick background, ECDSA signatures are randomized in two ways. So first is through some signing nonce that should be unique per signature and only known to the signer. Second, these signatures are malleable. So that means that if you give me any ECDSA signature, I can compute a second valid signature without any additional information. That's just because of the structure of points on an elliptic curve. So you can imagine some implementation bug that undermines the security of authentication. So for example, the token could choose some signing nonce using a weak source of randomness. And it's actually been shown with enough signatures, it's possible to recover the original signing key. So that would be bad. And you can also imagine some supply chain attack mounted against authentication. So for example, the token could try to hide the secret key for another site in its signature, essentially using the signature as a subliminal channel, very similar to the example where it was trying to hide information in a public key. So both these problems come from the fact that there's randomness inherent in these ECDSA signatures. We would be a lot better off if we could just use some unique signature scheme like BLS, but we're tied to ECDSA to maintain backwards compatibility with the U2F spec. The server is expecting an ECDSA signature, so that's what we have to give it. And so to address this, we introduced this new primitive we call Firewalled ECDSA signatures, inspired by recent work on cryptographic reverse firewalls. So we want the following two properties for these signatures. So first, the token shouldn't be able to exfiltrate any bits of information in the signature. This is based on previous work on subliminal free and subversion-resistant signatures. And second, the browser should learn nothing except for a valid signature. This is formalized more carefully in the paper. So I'm not going to walk through the construction in all its detail, but I'm just going to sort of explain at a high level how we get there from a basic U2F authentication flow. So it's just basic U2F. Server sends some challenge, token signs the challenge and sends it back. So ECDSA has this cool property where if the signer has R, if anybody else has G to the R, they can actually verify that the signing nonce R was used in that signature. And so what we would like is we would like to have the token have some R and the browser to have the corresponding G to the R so that the browser can check that the token is using the correct signing nonce. So how do we get this R and G to the R split between the two? Well, we can use the same collaborative key generation protocol that we used at initialization. This gives the token some random R that's unique per signature, and the browser some G to the R. So this takes care of the problem of the signing nonce, but we still have the problem of malleability. So remember, the token can send any one of 2 valid signatures back to the browser and to the server, and that can exfiltrate 1 bit of information through each authentication. And so what we do is we have the browser just randomly choose one of the 2 valid signatures each time. Simple, but it works. So first property we want is that the token shouldn't be able to exfiltrate any bits of information. And we get this by taking care of both sources of randomness, namely the signing nonce and the malleability. And second, the browser should learn nothing except for a valid signature. And here we see that because the browser's only learning this additional GDVR, which isn't really actually useful information. So this is all the protocol steps. There's some additional contributions that I don't have time to discuss now, but you can check out our paper if you're curious, including some cryptographic optimizations tailored to the token hardware, and flash optimized data structure for storing U2F authentication counters. There's one implementation consideration that I just want to touch on. So U2F doesn't require the browser to keep track of any state. So you can just plug your token into any computer and it'll just work. However, True2F does require the browser to keep track of some state for each token, in particular this master public key. So one really basic solution would just be every time you plug your token into some computer, it just gives the browser its master public key. And this provides some basic protection against implementation bugs. The browser can check the token's behavior from that point onward using this master public key. However, that's not very satisfying if you have some malicious token, as it can just give it some bad to sync this master public key across browser instances in the same way that you sync your bookmarks, for example. So we also implemented True2F on Google hardware, the evaluation that I've been promising you. So we knew there would be some overhead in comparison to traditional U2F, and our goal was to reduce this as much as possible. So on your left, you can see a Google development board that we use to get our evaluation numbers. And on your right, you can see a Google production token, not currently running True2F, but could run it in the future. Thank you. Okay. Oh, there we go. Okay, cool. Okay, so here we're looking at the cryptographic, at the latency of the authentication protocol, just looking at the crypto on the token in the browser. And we can see without any optimizations, True2F is pretty expensive in comparison to original U2F. So 446 milliseconds in comparison to 23. However, we can add a variety of optimizations to actually reduce this latency to 57 milliseconds in comparison to 23 milliseconds. So True2F is only about 2.5 times slower than traditional U2F. This looks pretty similar for registration as well. Just wanted to show one slide here, and authentication is the common case. So we were also curious what latency the actual end user experiences. So here we measured the time from when the browser receives some request to when the browser is actually able to respond. We found that a lot of time is actually being spent in the browser middleware as opposed to actually doing the crypto on the token and in the browser. And so the actual end user is not experiencing a 2.5x overhead. They're only experiencing additional 20 to 30 milliseconds of delay. And so True2F is only about 12 to 16% slower than traditional U2F for the end user. So in conclusion, True2F shows that we don't need to settle for untrustworthy hardware. True2F augments U2F to provide a strong protection against backdoor tokens in a way that's backwards compatible with existing U2F servers. It does this in a way that's practical to deploy and that it's performant on commodity hardware tokens. So U2F provides this really strong defense against phishing attacks as well as browser compromise, but True2F allows us to go one step further and not even have to trust the token. The paper and the code are online, so I would encourage you to check that out if you're interested, and I'll take any questions. Thank you. Yeah. There are lots of things you could You could also have like a trust on first use kind of thing, but yeah, you need a secure sync.
Is there any work? Is there any work not to rely on that?
We haven't thought too much in detail about this, so that would be really interesting future work. And I personally don't know if there's been research in that type of area. Yeah.
since I'm near the microphone. You mentioned on the initialization step, the collaborative key generation used 3 times fewer group operations than the protocol you based on. Was that a general improvement to that previous protocol, or were there some specifics unique to this case that allowed that improvement?
So the previous protocol used Pedersen commitments as opposed to just hashes. And so that normally wouldn't be like much of a problem if you were using, some reasonable, hardware, but on this small embedded device, that made a really big difference, especially given the cryptographic capabilities of this hardware. So for our specific use case, this was a big improvement for us.
I have a question. So you say that this new approach has an overhead in latency, but did you observe on any other overhead in like the power consumption of the?
So the power consumption isn't a huge concern because these devices are always just plugged into your computer. So we don't have to worry too much about that. We also didn't measure that carefully, and I would think that if we measured that, there wouldn't be a huge difference, but I also haven't measured that, so I don't know for certain. Yeah, there's some overhead in terms of like space being stored for our data structure for storing authentication counters, but that's not something I talked about here. So.
Okay, thank you.
Thanks again. That's great.